We want to begin this next section talking about operators and their relationship to one another, specifically the relationship of commutation. And then we want to get into talking a little bit of a surprising consequence of quantum mechanical thought, and that is quantum entanglement. If we were to look at and measure the values of two different observables, we'll call them A and C, and those observables correspond to operators A and C that we symbolize with capital letters. They can be simultaneously determined if and only if, that's what IFF stands for, the measurement process used does not change the state of the system. This is only true if the order of measurement in experiment or of operation mathematically doesn't matter. Otherwise, the system on which the two measurements is carried out is not the same when a second measurement is carried out. So if order is important, then measuring C then A will not give you the same value as measuring A and then C. What does this mean mathematically? If we've got a wave function that is an eigenfunction of both A and C, then operating on a system first with A and then with C would give us this. So we operate with A, we operate from inside to outside, we operate with A, we get eigenvalue A. Eigenvalues can be pulled out, factored out in front, and then we operate with C and we get A times C. Same would be true in reverse. We operate first with C, we get eigenvalue C, we pull that out front, we operate with A, we get A times C times the original wave function. So if both operators have the function as eigenfunctions, then order of operation doesn't matter, and those operators are said to commute with one another, and those are measurables. Those operators correspond to observables or measurables that can be known about a particular system simultaneously. So if two operators commute, then measuring with one first then the other produces the same result of measuring with the other first and then the original. We can rewrite that the difference between the two measurement schemes is zero. There's no difference in values by measuring those in opposite orders. If the operators don't commute though, if measuring C first and then A gives different values than measuring A first and then C, because A changes the system, because the system is not an eigenfunction of A but becomes an eigenfunction of A, as we discussed earlier during the postulates, becomes an eigenfunction of A when it is measured with A. Remember that non-eigenfunction can be expressed as the sum of eigenfunctions, and when we measure with A, it changes the system to one of those eigenfunctions. So if order matters, there's a difference between measuring one and then the other, and we call that the commutator. It is the difference times the original wave function between the result of measuring in opposite order with two operators. Only measurables, only observables whose operators commute can both be known at the same time. So as an example that will work in class, we'll go ahead and determine whether momentum and kinetic energy of a particle can both be known simultaneously. And then we'll determine whether momentum and total energy of a particle can both be known simultaneously. If you want to try this out, get your books out, write this question down, look up those operators. You can try that out on your own before class, and we'll give it a shot next time. But before we do that, I want to go ahead and look at a experimental version or experimental evidence for this particular phenomena. The Stern-Gerlach experiment, very interesting experiment. I encourage you to read the history behind it in your textbook. But the Stern-Gerlach experiment, done in 1922, takes a beam of silver atoms that all travel in one direction and pass them through a magnetic field that has a constant value in the XY plane, but varies linearly with the Z coordinate. So the way I'm going up and down with the cursor right now would be the Z axis. So the atoms are then, after being passed through that magnetic field, detected somewhere past the magnet. Since silver atoms have an unpaired electron, they have a magnetic moment associated with their electron spin. So the atoms are going to be deflected by the magnetic field in the Z direction by an amount that depends on the Z component of the spin of the electrons. Depends on how the magnetic moments are oriented to one another, basically. Now, if the orientation of the magnetic fields is random, as we would expect, thinking classically, then we should get a wide range, a continuous range, of silver atoms banging into our plate back here, our detection plate. But what we actually get is two big piles of silver atoms. All the silver atoms are deflected by the same amount in either the north direction of the magnet or the south direction of the magnet. To put this in terms of mathematical operators, we could say that the operator associated with measuring the magnetic moment in the Z direction of silver atoms traveling in the Y direction does not have the full system as an eigenfunction, but is the sum of two eigenfunctions with eigenvalues that are equal but opposite in sign. And so the wave function of the whole system is a linear combination of those two functions. And after doing this experiment for a while, we let this run for a certain amount of time, we realized that the amount of silver deposited here is the same as the amount of silver deposited here. So the coefficients on the functions in that sum that make up the overall wave function are going to be equal to one another. All right, so we summarize that mathematical result here on the next slide. And we can write the wave function this way, where alpha and beta are wave functions that are both eigenfunctions of the operator we described, measuring the Z component of magnetic moment. And the sum of them is not an eigenfunction because two possible answers are observed. And assuming that they're both normalized, the sum of the squares of these coefficients has to be 1. And because, like I said, over time we see the same amount, then each of those constants is actually the square root of 1/2. So the question that comes up, we had the magnet oriented along the y-axis. What if we had it oriented along the x-axis? Even better yet, what if we took the two separate beams and placed magnets along them and separated them by x-axis? Does it matter if we separate them by x first and then z, or by z first and then x? In other words, do the operators measure the z component of the magnetic moment and measure the x component of the magnetic moment? Commute. And so how would we tell that experimentally, and how would we tell that mathematically? Well, experimentally, we could conduct a Stern-Gerlach experiment as shown, pass one of the split beams through a magnetic beam in the x direction. It'll split again, and then pass one of those beams through another z direction. Since we already separated the silver atoms by z direction at first, if these operators commute, we shouldn't get a separation the second time we pass it through the z direction. If they don't commute, we'll get a separation the second time through the z direction. Mathematically, we can already guess how this is going to come out. The original wave function of the particles was not an eigenfunction of the z component magnetic operator. So operating on it with a z measurement changed the system. It changed from being a linear combination to being one eigenfunction for each beam. Since measuring changed the system, the order of operation is going to matter, which means those operators are not going to commute. So without even looking at their mathematical form, we can tell that we can't know the z component and the x component for a particular silver atom both at the same time. Measuring the z component and then measuring the x component is going to reset the z component. And this is what we mean. We take that beam, we pass it through a z directional magnet, split them, take that beam and pass it through an x directional magnet, split them. If order of operation didn't matter, we wouldn't see a split here and here. We'd see all deflection one direction or the other. But since it splits again, we were correct in our hypothesis that we would see that these operators would not commute. Now, the most famous application of this idea of commutating and non-commutating operators is the Heisenberg uncertainty principle, because x, position, and momentum cannot both be known at the same time. In other words, to say that mathematically, the operators associated with measuring position and with measuring momentum do not commute. As an illustration for this, the free particle wave function, we showed that the plane wave is an eigenfunction of the momentum operator, but we couldn't find out anything about the position. We could only calculate a probability of finding it in a particular area. And even then we had to assume a length of that particle in the box. So if it's a free particle, we're even having to fudge in to get even the slightest bit of probability information about the position. So anytime momentum is known exactly, position is completely unknown. And the reverse is true. If position is known exactly, momentum is completely unknown. Now, if we find a wave function that's a superposition of several plane waves in this form, where we've got just a certain number of plane waves, the more terms that are in the sum, the smaller the uncertainty of the position becomes. However, each term is a different eigenfunction of the momentum operator with a different eigenvalue, so the more terms in the sum, the more possible values for momentum, and the larger its uncertainty becomes. And so we can improve our understanding of the x of the position of the particle, but each step we take in the wave function to improve that understanding, we lose certainty for momentum. Heisenberg was able to show mathematically in his most famous paper that regardless of the wave function or the system being considered, the product of the uncertainty of the momentum and the uncertainty of the position has a bare minimum value of 1/2 h bar. Now that's a pretty small number. 5 times 10 to the minus 35 joule seconds. But in systems that are small, this can be significant. While this is the most famous of the quantum uncertainty principles, the concept applies to any pair of observables or measurables whose operators do not commute. Another one that's famous that caused a discussion or argument between Einstein and Bohr was the uncertainty with respect to energy and time. Alright, so we've got a couple of examples that we can work related to these. You guys can pause the video now and write these down, and we'll try these out in class. Here is another one, and like I said, go ahead and pause the video, write these down, and we will work these problems in class. Additionally, the textbook in section 6.4 does a pretty good job of applying the uncertainty principle mathematically to the particle in the box. We're not going to take the time to go over it here in class, but it wouldn't be a bad idea to read through that. It might give you some hints on studying for test problems or questions, and maybe even a little bit on the homework.